Okay, I still don't like what I've got here. I didn't leave myself enough room to write the delta S. In any case, our F dot delta S is what? Well, here's our F, our 3/4 I plus square root of 3 over 4j. Well, that's it. And we're dotting that with our delta S vector, which is just our magnitude delta S multiplied by the unit tangent vector. Unit tangent vector being this, but more accurately expressed as -1/2 I plus the square root of 3 over 2j. And you know how to get that unit tangent vector, so that's not a problem. And then that times delta S. So here's our unit tangent vector times delta S. So all this is our delta S vector, maybe. All this is our delta S vector. Okay, well, when we do this, we find that the dot product is 0, so that this whole thing is 0. And I didn't really think that was going to happen, but it did. And we go on with an example where I just change the function by a little bit. I think I square the y here, and then this doesn't happen anymore. Just a coincidence on the unit circle. Actually, the same thing would happen on any circle centered at the origin. Okay. Still, we're going to take this on and see how we would develop an integral that gives us the integral of this function all the way around here. We know that the integral is 0 simply because the unit tangent is always, in this case, perpendicular to the vector field. Okay. But that's the only reason it's 0. There are other reasons it could be 0. And I'll just mention, if your function is a gradient, then the integral around any closed curve has to be 0. That's the definition of a conservative vector field. And turns out physics students just recently had a problem on their homework that asked to verify whether a certain field was conservative or not. And this is kind of the answer. If it's a gradient, then yes. If not, it isn't. Just a preview. That's come in the following week's assignment, the week assignment after the one where we're doing this. Okay. Well, now on a typical interval, and let me just write a little note that what we think of doing now is we partition this interval and do this F dot delta S calculation for every partition on the interval. Now, physics students will recognize that if F is force and delta S is displacement, then F dot delta S is the work done, corresponding by that force as we displace from, well, over this displacement. Okay, so what we do is we partition the interval 0 less than or equal to t less than or equal to 2 pi and consider a typical increment. Still didn't leave myself enough room. Someday I'll learn, but I doubt it. Okay. So on a typical increment of your partition, you're going to have some sample value for t, and we're going to call that t star. So how are we going to do the F dot delta S on that for that particular t interval? We're going to multiply f of x of t star, y of t star, whatever our function is, whatever our x function is, whatever our y function is. We're going to evaluate this at the sample point on that interval to give us a typical value of the f. Remember, this is a very tiny integral, and we're going to take the limit as the width of the increments approaches 0, so that any inaccuracy, and assuming that the vector function has this value over the whole interval, becomes irrelevant. Okay, and then a delta S at t star. So what's our delta S for given t star? It's going to happen then that x of t and y of t are cosine t, sine t. So we're going to have f of cosine t star, sine t star, dotted with our delta s of t star. Well, our delta s of t star is just our unit tangent vector times delta s. Now the unit tangent vector is evaluated at the t star. Okay, over here what did we do? T was equal to pi over 6. We found the value of f. We found the value of our unit tangent vector. Okay, well, we can do that for any value of t, including the value t star. So that's what we're going to put in here. I could have written that this is unit tangent vector evaluated at t star. Can't read that, but now it says t of t star. Okay, well, what is f of cosine t star, sine t star? Just plug in x squared for the I, xy for the j component, and we get this. I'm not going to read that to you, you can do that. And our unit tangent vector, well, our general unit tangent vector is just r prime of t divided by the magnitude of r prime of t. R prime of t is negative sine t I plus cosine t j. Since x is this, y is this, our r prime is going to have x component equal to the derivative of this, y component equal to the derivative of this. Just work it out. This is what you get. Evaluated, of course, at t star. And then we multiply that by our magnitude delta s, because we got our vector t of t, our t of t star. Multiply that by delta s. We have our displacement vector on the curve. Okay, well, we do that, we get this. Again, I'm not going to read it to you. You can do the dot product. That's really easy. And we factor out the sine of t star. Actually, yeah, I just factor that out, but it's clear that actually this and this are equal and opposite, so I really didn't have to factor anything. It's clear that everything came out to be 0. Okay, so it turns out that this isn't a real interesting integral, but in general, this is the kind of thing we're going to do. Now, this is the typical interval. If this came out something that wasn't 0, we would actually want to do the integration. And we would think of a Riemann sum approaching the limit and think about what our integral would be. It'd be fairly straightforward. We're going to do that for a slightly modified function in the next video.